Question number 11 from May 2017, HL Paper 1, Time Zone 2. In part A, we need to solve this equation where x is between 0 degrees and 180 degrees inclusive. So what we need to do to solve this equation is use the compound angle identities for sine and cos. So I can write 2 sine x plus 60 degrees as 2 multiplied by inside the bracket sine x times cos 60 plus sine 60 times cos x, and this will equal, and using this identity I can write cos x plus 30 as cos x times cos 30 minus sine x times sine 30. From here this 2 remains as it is, and inside the bracket we have 1 upon 2 sine x plus root 3 upon 2 cos x, since cos 60 is 1 upon 2 and sine 60 is root 3 upon 2. This will equal root 3 upon 2 cos x minus 1 upon 2 sin x. So cos 30 is equal to root 3 upon 2 and sin 30 is equal to 1 upon 2. From here we can expand this bracket, so the 2's will cancel out. So we're left with sin x plus root 3 cos x is equal to root 3 upon 2 cos x minus 1 upon 2 sin x. From here we can group our like terms together. So we're left with sin x plus 1 upon 2 sin x is equal to root 3 upon 2 cos x minus root 3 cos x. Now if we add these two together, this will give us 3 upon 2 sin x, and root 3 upon 2 minus root 3 will give us negative root 3 upon 2 cos x. So from here we can cancel these 2's and we can move cos x to the left hand side to get sin x upon cos x, and we can move 3 to the right hand side to get negative root 3 upon 3. From here sin x upon cos x is equal to tan x, and I can write this as negative 1 upon root 3. These two expressions are exactly the same, so we need to solve tan x is equal to negative 1 upon root 3 without a calculator. Now firstly I will draw the magic triangle, also known as a 30 60 90 triangle. So this angle is 60 degrees, this angle is 30 degrees, and this angle is 90 degrees. So this side length is root 3, this side length is 1, and this side length is equal to 2. So tan of 30 degrees, this will equal opposite upon adjacent, so 1 upon root 3. So we know that tan of 30 degrees is equal to 1 upon root 3, but we need negative 1 upon root 3. Now this is where a good understanding of the unit circle helps. So I will draw the unit circle. So this is a rough unit circle. Now 30 degrees is right here, somewhere here, and tan of 30 degrees we know is 1 upon root 3. Now what we need to know is that tan is negative in quadrant number 2 and 4. So if tan of 30 is 1 upon root 3, then 180 minus 30, which is 150 degrees, somewhere here, this will give us negative 1 upon root 3. This is something that we need to know, and a good understanding of unit circle helps, but x will equal 150 degrees. Now for part B, it says show that sine 105 degrees plus cos 105 degrees is equal to 1 upon root 2. So for part B, what we can do is I can write 105 degrees. 105 degrees can be written as 60 degrees plus 45 degrees. So we need to make use of these identities for sine and cos. So sine 60 degrees plus 45 degrees is equal to sine 60 times cos 45 plus cos 60 times sine 45. So this will give us root 3 upon 2 times root 2 upon 2 plus 1 upon 2 times root 2 upon 2. We need to know our trigonometric ratios for this. Now from here, this multiplication root will give us root 6 upon 4, and this multiplication will give us root 2 upon 4. So we can add these together to get root 6 plus root 2 upon 4. Now similarly we need to use this identity for cos. So cos 60 degrees plus 45 degrees is equal to cos 60 times cos 45 minus sine 60 times sine 45. So from here this will give us 1 upon 2 times root 2 upon 2 minus root 3 upon 2 times root 2 upon 2. Now over here I will just add a step. So 1 upon 2 times root 2 upon 2 will give us root 2 upon 4 minus root 3 upon 2 times root 2 upon 2 will give us root 6 upon 4. So we can subtract these to get root 2 minus root 6 upon 4. So finally we can add sine 105 degrees plus cos 105 degrees to get root 6 plus root 2 upon 4 plus root 2 minus root 6 upon 4. So from here positive root 6 and negative root 6 will cancel, and root 2 plus root 2 is equal to 2 root 2. So from here we can cancel this 2 to with this 4 to get 2. So we're left with root 2 upon 2. From here root 2 upon 2 can also be expressed as 1 upon root 2, and I will explain how. So I can write root 2 as 2 to the power of 1 upon 2, and 2 is just 2 to the power of 1. From here I can use the laws of exponents and write this as 2 to the power of 1 upon 2 minus 1, from where this subtraction will give us 2 to the power of negative 1 upon 2. So I can write this as 1 upon root 2. So that is how we find this from root 2 upon 2. Now for the final part C, it says let z equal 1 minus cos 2 theta minus I sin 2 theta, where z is a complex number and theta is between 0 and pi inclusive. In part C1, we need to find the modulus and argument of z in terms of theta and express each answer in its simplest form. So what we can do for C1 is that firstly we can separate the real part and the imaginary part. So the real part is 1 minus cos 2 theta and the imaginary part is sin 2 theta. Now to find the modulus of z, this will be the square root of 1 minus cos 2 theta whole squared, the real part squared, plus negative sin 2 theta squared, the imaginary part squared. That is how we find the modulus of a complex number which is in rectangular form or Cartesian form. So from here we need to expand this bracket. So this will give us square root, under the square root 1 minus 2 cos 2 theta plus cos squared theta, and this will give us plus sin squared 2 theta. Now from here we can use the Pythagorean identity, and cos squared 2 theta plus sin squared 2 theta, this will be 1. So this stays as it is. From here I can add these ones to get the square root of 2 minus 2 cos 2 theta. From here I have factorized 2, so I'm left with the square root of 2 1 minus cos 2 theta. Now from one of the identities right here, what we know is that cos of 2 theta is equal to 1 minus 2 sin squared theta. So I can rearrange this equation and get 2 sin squared theta is equal to 1 minus cos 2 theta. So I have replaced this with 2 sin squared theta, which gives us the square root of 4 sin squared theta. So if we take the square root of this we left with 2 sin theta, and this is the modulus of z. And now to find the argument, what I've done is I have let the argument of z equal a. So tan a is equal to the imaginary part negative sin 2 theta upon the real part 1 minus cos 2 theta. That is how we find the argument of a complex number which is in rectangular or Cartesian form. So from here I can use the double angle identity for sine and write this as negative 2 sin theta cos theta, and I can replace cos 2 theta with 1 minus 2 sin squared theta using this identity. So from here the numerator stays as it is, and 1 minus 1 cancel, and negative times negative makes it positive 2 sin squared theta. From here the 2's cancel out and one of the sin theta cancels, so we left with negative cos theta upon sin theta, which is equal to negative cot theta. Now this is where the question gets challenging, because this is not in the formula booklet, but one of the relationships between cot and tan is that cot theta is equal to tan of pi on 2 minus theta. This is a relationship that we need to know to solve this question. So I have replaced cot theta with tan of pi on 2 minus theta. From here we also need to know that negative tan of theta, this is equal to tan of negative theta. This is another relationship we need to know. So I have taken this negative sign inside the bracket, so we left with tan of a is equal to tan inside the bracket theta minus pi on 2. I have taken this negative inside the bracket. Now to solve for a, what I can do is I can take arctan. So a is equal to the arctan of tan theta minus pi on 2. So from here arctan and tan cancel and we're left with a is equal to theta minus pi on 2. Now since a was also the argument of z as assumed earlier, we can write that the argument of the complex number z is equal to theta minus pi on 2. Now for the final part, it says hence find the cube roots of z in modulus argument form. So what we can do for the final part is, hopefully we also know that a complex number z can be expressed in the form r cis theta, where r is the modulus of the complex number and theta is the argument of the complex number. So we already found the modulus and argument of z in the previous part. So I can write z is equal to 2 sine theta cis theta minus pi on 2, where 2 sine theta is the modulus of z and theta minus pi on 2 is the argument of z. From here, to find the cube roots, we can raise both expressions to the power of 1 upon 3. This will give us the cube roots. So we raise this entire expression to the power of 1 upon 3. Now from here, we need to be familiar with De Moivre's theorem. So applying De Moivre's theorem, we get 2 sine theta to the power of 1 upon 3 cis. Now we need to divide the argument with 3 and also add 2k pi. So we left with cis theta minus pi on 2 plus 2k pi upon 3 as the argument. Now you do need to be familiar with De Moivre's theorem to understand how we get this. In the next step, I have just made some simplifications. So I have written this as 2 to the power of 1 upon 3 multiplied by sine to the power of 1 upon 3 theta cis theta minus pi on 2 plus 2k pi upon 3. So, and where k is equal to -1, 0 and 1. What this means is that when we plug in these values for k, we will get our cube roots of z from this main expression. And we don't need to simplify this further. This is what the question has asked for. And so this is the answer to question number 11.